And so in addition to the Carnot cycle and the Stirling engine, let's look at some practical applications of these types of thermodynamic cycles. And that would be the combustion engines that we use every day. So the gasoline engine, the four-stroke engine, and the diesel engine. So in terms of the Carnot cycle, we've drawn these expansions and compressions. Two are isothermal, two are adiabatic. So that's sort of the perfect system. And so we notice that we have these expansions. How do we make that practical? How do we turn that into mechanical motion? And so mechanical motion is pushing things or turning things. And so we push a piston and then it turns a crank. So just like you can take a handle and turn a crank, we make a piston turn a crank. And that's inside your car and truck. There's a thing called the crankshaft. It's just the strangest looking shaft. It's got all of these little cranks all hooked together. And so all the different pistons, if you have an 8-cylinder engine, there are 8 cranks. Or they might have 2 paired to 1 crank. And that's what like a V-twin will have on a motorcycle. The 2 pistons are pushing on the same crank. So we turn that expansion of gas into mechanical energy. So we go from chemical energy to mechanical energy. And then we could hook that to a generator and go from mechanical energy to electrical energy. And then we could run that electricity through a hot wire and make light. So we just really are converting energy from one form to another. And all of those conversions have less than 1 efficiency. So when we get to the last fifth of the course, we'll talk about energy conversions, sources and sinks. And so we'll talk about chemical energy, mechanical energy, electrical energy, light or photonic energy, even gravity. So we'll cover all the different forms of energy and then how they're converted one to another and the efficiencies for all those processes. So I think it's sort of an exciting end to the course where we get into all the different types of energy that we use and their conversions. And so these expansions are pushing on the piston, that's turning the crank, that's giving us mechanical energy. But this Carnot cycle is sort of an idealized cycle. Why do we still use it? Well, because there's 2 reasons. It's the maximum theoretical efficiency. So the Carnot cycle is the perfect cycle. And everything's reversible. And so we're able to get the maximum amount of work for the minimal amount of heat. It's not perfect though. What would make the Carnot cycle perfect? Where we talked about this limitation. It's like the second law of thermodynamics. No process is possible where you have the perfect conversion of heat into work. On one leg, that isothermal expansion where we have heat in and that's turned into work out, and those numbers match. They're equal and opposite. Because it's isothermal, the internal energy is the same. It's 0 change in internal energy. So that looks like a violation of that second law of thermodynamics. Okay, but the second law is really talking about this whole cycle, because we have to do work on the system, and so when we push on the system and compress it to reset it, we have to sink heat out. So it's giving heat out that's lost. So we put in that heat, and then some of that heat comes back out. It doesn't get converted into work. See, so it's not a violation of the second law. This cycle shows that even though we put in heat and we get work out, we also have heat that comes out during that isothermal compression. Now the way to make this cycle perfect, in other words, 100% efficient, think about the temperature equation for efficiency. What could you do to make it 100% efficient?
Either make it really hot and
infinitely hot, yeah.
or really cold, or
really cold. And so if we could get that cold reservoir to be 0 Kelvin, then we would absolutely have a perfect engine. And so because of entropy, we can't get that. We can't get that down to 0 Kelvin. We can't put it in contact with something that has no entropy and get it in contact with 0 Kelvin thermodynamically. So we're not going to be able to get a perfect engine. So let's look at these specific uses of cycle problems or the specific application of them. And here we have the 4-stroke gasoline engine. So that efficiency is between 0.2 and 0.3. And so let's go through, when we talk about a 4-stroke engine, what do we mean? And so if you think about those pistons, you have a push and a pull, a push and a pull. Now for the Carnot cycle, we just have a push and a pull. It's just 2 strokes. You push out and you pull in. We have 4 legs, but really there's 1 expansion, 1 compression total. For the engine, the 4-stroke engine, the piston goes down and back 2 times. So there's a down and an up. That's 2 strokes, and then down and up again is 2 more strokes. So 4 strokes. So the crank turns around twice for each cycle. So we have the cycle diagram up in the upper left, the PV plot, and those different points. Notice we have more points. We don't just have A, B, C, and D. Now we have E added in there. Okay. And so from E to C, so if you look at this from E to C, what's going on? Look at the volume. So in this plot, you're going to have to really follow the volume of what's going on. And when the volume's increasing, that means the piston's going down. And so from E to C, the piston's going down, and the intake valve is open. So you're filling the piston with what? Air and fuel. Okay, so an air and fuel mix. And so this would be coming from the carburetor or from a throttle body, which is like a fuel injector with the air. So it sprays the fuel and makes a mixture of oxygen, nitrogen, and gasoline vapor. All right, so we pull that down into the piston. So notice there's no pressure change. So this is at the vacuum of the engine. We pull that piston down and it sucks the air and gasoline in. And then we close that valve. So when we close the intake valve, now the piston chamber is sealed up. And we do a compression. This happens really quickly. We'd like for it to be adiabatic. Adiabatic would be the best scenario. It's not exactly adiabatic. Some of that heat of compression does leak into the engine body, so that's why it heats up. Okay, but it's fast, so it's I may be closer to adiabatic than it is isothermal. Okay, so we compress that that air-gas mixture, and so that's C to D. So that's the compression of the engine. So we have intake stroke, compression stroke, and then what happens to cause the pressure to jump up? So we're at the minimum volume now, and the pressure dramatically increases.
Ignite the heat.
Yeah, we spark the spark plug. Okay, so when we spark the spark plug, that's D to A. Okay, so notice D to A to B, that's what this power stroke is. So we spark the spark plug at D, and then you have this huge jump in heat and pressure, and then we have the power stroke. So A to B. So that's pushing down on the crankshaft with power. Okay. So we burn the gas, we have this adiabatic expansion, because again, it happens quickly. It's not exactly adiabatic, which is why the engine heats up. Okay. And then we reach the bottom of the piston chamber, so we're fully extended. And so then the pressure drops dramatically, B to C. So what happens with B to C? We open that exhaust valve, and those hot gases, the pressure drops and it shoots out to the exhaust. Okay, and then we assist that by doing an exhaust stroke, C to E. So now the volume decreases again, but there's no explosion or anything. That's just the expulsion of the exhaust gases. So the exhaust stroke, the piston comes back up with the exhaust valve open. All those hot combusted gases are pushed out to the exhaust manifold, which goes through the catalytic converter. There's a lot of unburned hydrocarbons in here, and so those hydrocarbons land on platinum rhodium surface. And when you take away 1 degree of freedom, the reaction rate goes up. Okay, so if you think about molecules trying to find each other in 3 dimensions, if you make that in 2 dimensions, it's a lot faster. And so this platinum rhodium catalyst, the hydrocarbons will land on that surface because a lot of the unsaturated bonds, like the double bonds, they interact with the metals. and oxygen will be able to attack that molecule. Oxygen can land on that surface too, and they can migrate around on that surface. And so you're actually finishing the combustion on the catalytic converter. So you increase the reaction rate, but it doesn't change the delta H. So it's still a very exothermic process. So that catalytic converter can come up to the combustion temperature. It's really hot. So this metal is plated on ceramic beads, put into that case, and then that's why you don't want to drive on really dry grass in Texas in August. Because your catalytic converter is at essentially combustion temperature or close to it, and it will catch that grass on fire. A lot of our grass fires are people driving over really dry grass in the heat of the summer. And you know, you don't even have to be a smoker and throw your cigarette out. Just driving over dry grass, you can catch it on fire. So anyway, that's sort of a side trip, but prairie fires are a problem because the catalytic converter is super hot. You know, if those gases, unburned hydrocarbons, just blew out the tailpipe, you know, they would take their heat with them. But because we want cleaner air, this is a way to completely combust those uncombusted gases in the catalytic converter. So mostly CO2 and water come out of the tailpipe. And nitrogen oxides. We try to reduce that, but as the engine temperatures get hotter, we start to see some oxidation of nitrogen gas inside the cylinder. And so we have nitrogen oxides coming out. And we want to keep the sulfur in our gas low because sulfur oxides make acid rain. And so that the sulfur oxides turn into sulfuric acid in the tailpipe and in the clouds. So if we could remove the sulfur and reduce the NOx's and combust our hydrocarbons, we can have cleaner exhaust. This has been a dramatic change in terms of improvements, and so photochemical smog is still an issue, but it's a lot less than it used to be because of the catalytic converter. So that's the full 4-stroke engine. Now we do this again. We did that exact exhaust stroke, so we're at E, and then we close the exhaust valve, open the intake valve, and start again. So when we open the intake valve, we pull in the intake with again, an expansion of that cylinder, and then we close off that intake valve, compression, spark it, power stroke, then do the exhaust and start over. So if you think about this, that power stroke has to drive 2 turns of the crank. And so in the old tractors, they call them the Poppin' Johnnies, they had a big flywheel on there because you need some inertia. And so that piston would push the crank and come back up, and then you had the exhaust stroke and the intake stroke. And it would push the crank, so it would go pop, pop, pop. And so as you maybe see one in a parade, if you're ever in a small town, you see a parade, you see this green tractor with a big wheel on the side, and that wheel's spinning, and that's the flywheel. So it's going pa, 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 and that wheel's turning to keep the piston going. If you don't have that inertia, then it will go pop, stop. Because when it tries to get that turn and overcome all that friction, and especially get that compression step, the compression step really resists that piston. You're compressing that gas. If you don't have enough inertia to get that compression to take place, then the engine stops. And we saw that with the Stirling engine. I would heat up that side, I would try to spin it, and it would go a couple of times, and then it would stop because it's trying to compress that gas, and it didn't have enough inertia. So you saw that big wheel on the Stirling engine. That was my flywheel. Let's look out at the diesel engine. I'm going to keep the same pictures, but essentially we could mark out the spark plugs because the diesel engine has a higher compression ratio, and it squeezes the diesel and the air mixture enough that you get auto ignition. So just by compression, it's enough for the diesel fuel to ignite. And this is this is just what I talked about verbally, but in words. And so if you just had the notes, you could see what's going on. So then the diesel engine has a little bit different shape to it. See down here in the bottom left, the diesel cycle. And so for the diesel engine, you could mark out the spark plugs, and they have just a little hot wire in there called a glow plug. It doesn't spark, but when the engine's cold, it provides a little bit of heat to cause it to auto-ignite. Because the diesel engine has a higher compression ratio, it pushes it higher on the PV plot. And so we have the intake, E to D, and then we have the compression, D to A. So we're way up here, And in fact, modern diesel engines have increased the fuel injection pressure dramatically. So now we wait until the piston is all the way at the top, and then we start spraying the fuel in with the injector. And it's spraying in with the fuel injector into a oxygen-rich environment, high pressure, and it starts to burn instantly. So we're spraying in the fuel, and it's burning right away. And so we're already starting to do the power stroke, and we're still spraying fuel in there. So we're adding heat while we're doing that power stroke. So we have an isobaric leg on this one. If you'll notice, A to B is isobaric because even though we're expanding the volume, we're adding in moles of gas and raising the temperature. So we're raising temperature, adding in moles of gas, and expanding at the same time, and it keeps the pressure constant. And again, these are idealized, so this would be an ideal situation where we're keeping the pressure constant. And then we stop spraying in fuel, and then we continue to do the power stroke, which is an adiabatic reversible expansion. So that power stroke is from A to B down to C, which is shown down here at the bottom, ABC. And then the exhaust, we pop that exhaust valve open, and it drops the pressure from C down to D, and then we push all of the burned gases out, D to E. So once again, it's a four-stroke engine still, but it's using diesel fuel, high pressure fuel rail, spraying it in. The reason diesels have gotten quiet, have you noticed? I don't know, maybe you haven't noticed, because maybe it's been within your lifetime, but 10, 15 years ago, diesels were much louder than they are now. They've done two things. They've moved this fuel injector rail higher in pressure, and so the sound is a lot higher pitched, and so you don't notice it as much. They used to rattle very badly, okay, and now they've moved the sound of the fuel injection system. Because it's at high pressure, it's much quieter and much higher pitch. And then they stuff air in there. So they don't operate this intake at atmospheric pressure. They actually have a turbo that stuffs air in there. So they put more air into the cylinder, and they push in the gas or the diesel at higher pressure, and so you get a more efficient engine out of it. So they've improved the diesel engine even more. Now it's up to around 35%, which we notice from the Carnot cycle is still pretty good. So this is what I pretty much talked about, but in words, so that you can see that in the notes. There's one other type of engine that we use regularly, and that is the jet engine or gas turbine engine. And so here we have it's kind of difficult to picture because we think now in pistons. I mean, all the engines we've talked about now have distinct expansion and compressions with pistons. Well, now we have fan blades. And so the pitch of the fan blades can create compression. Okay, and so this compressor part, if you see up there on the turbine, the compressor, the pitch of the fan blades is pretty aggressive, meaning it's scooping lots of air and stuffing it into the system. So it's the compressor side, I call it hungry. Okay, it's grabbing lots of air and compressing it in the middle of the engine, and that's where we add the fuel. So in that high pressure area, we add the fuel, it burns, that's the heat in, and then it exits out the back. And we want to harvest some of that by pitching the fan blades less aggressively. And so the expanding high pressure gases have to push the fan blade out of the way. If we had it at a higher pitch, it would be easy to push the fan blade out of the way. So we close them down, and it's harder to push them out of the way. And so we're able to harvest that torque on those hot expanding gases. And so we have the intake, which is the compression cycle. So this compressor piece governs this leg here. The fuel burning, kind of like our diesel engine, we spray in the fuel at high pressure and it burns and adds temperature and adds moles of gas. And then this turbine, the exit part gives us this expansion. And then the heat out, it just blows out the back. And so we've got air coming in, fuel coming in the top, and exhaust going out here. And it's just constantly, like the whole engine is running all these legs at the same time. So it's not like a four-stroke engine where you have a power stroke and an exhaust stroke. Okay. So let's look at this next one. It might be a little. So here's a picture of the engine. You can kind of see the different blades. So whenever you see jets, you see that intake. You know, you're looking at the front of a jet engine, and you see these blades. You see how they're pitched. They're very, I would say, very hungry. They let air in quite easily, and then we change the pitch of those blades gradually so that you get huge compression here in the middle. They spray in the fuel, and then it pushes against those, you know, the power turbine back here. And then this hot air is coming out. You could put in more fuel here and create, if you have, you know, the structure of, like if you have a flare at the back and you have expansion of the fuel, it can impart more force to that structure and give you more thrust. And so that's what we call afterburners. So you can have the turbine going, and then you can also spray in extra fuel at the back. It's very inefficient, but it does give you a boost. And so that's what our military jets have. We don't have afterburners on our commercial jets. I think it would be very uncomfortable for the passengers. So pin your head back. And plus, I don't think we could carry enough fuel in those things to effectively use an afterburner. So that's great for transportation, but we can also use this same pretty efficient engine to turn a generator. And so now on a lot of our methane gas power plants, we'll use methane fuel, and over here we'll have a generator. And it'll give us electricity. And you can go by Roan's Prairie and see that plant out there at Roan's Prairie. That's a natural gas turbine electrical plant. And so they're just pumping natural gas into turbine engines, spinning a generator with that. The nice thing about those is they can be brought online very quickly. You know, it doesn't take a lot to start one of these up. Okay, so they do load leveling. Like they can run a coal plant or a nuclear plant at its max efficiency, and then if they need a burst of energy, like in the morning when everybody turns on their heaters in the winter, or AC in the summer, they need its huge demand at 5 in the morning, then they can fire up that natural gas plant. And then in the afternoon, a cold front comes through, and a cool front, people turn off their AC, or it warms up and they turn off the air conditioner or heaters, then that plant can be brought down and stopped, so you're not wasting natural gas. Again, we'll talk more about that in the last part of the course. Yes.
Do you know the efficiency for turbine?
The gas turbine? No, I don't. And because I don't know the temperatures. And so if you could figure out what their max and min temperatures were, then you could calculate the maximum efficiency. So again, the Carnot cycle is really useful for that maximum theoretical efficiency. And so it's none of these are perfect Carnot cycles, but we could say that their maximum efficiency would be that hot and cold temperature in this equation. So it's a great estimate. It's like, what possible efficiency could we get out of this? If you tell me the combustion temperature inside the gas turbine and the cold temperature of the air coming in, then that's going to be your range. And so then you think about the cold air up in the upper atmosphere, your efficiency gets better up there because of the difference between the cold and hot temperatures. So. All right, so now that's it for the content of the course. We can go to Q&A on Friday's exam, and so we'll stop the video for that. Well, who's missing? No, we're all here, so let's go.